Mars has long been the symbol of humanity's search for life beyond Earth, but far from the Sun, hidden beneath a frozen shell of ice, Europa may hold something even more important: a vast ocean, chemical energy, and perhaps the conditions life needs to begin. If the next great discovery in space is not on Mars, but on one of Jupiter's moons, everything about the search for life could change. If this kind of space documentary is interesting, please like the video, subscribe to the channel, and stay with this journey. The search for life beyond Earth begins in a careful way. It begins with a method. Scientists study life on Earth, then ask what parts of that example seem essential and what parts may simply reflect local history. From that work comes astrobiology, the study of the origin, evolution, and distribution of life in the universe. Astrobiology does not assume that every living thing must resemble Earth life in detail. It does, however, use Earth as the only confirmed example of biology. That limitation shapes every decision. The question is not where life would seem most dramatic, but where conditions appear stable enough and persistent enough for biology to begin and continue. This search logic explains why Europa often stands beside Mars, and why some scientists regard Europa as the more significant target in the search for living systems. Mars remains one of the worlds of planetary science. Its dry valleys, delta deposits, lake sediments, altered minerals, and ancient rock surfaces show that it once held environments very different from the cold and arid planets seen today. Evidence from orbiters and rovers indicates that parts of early Mars contained liquid water at the surface, and that some regions remained habitable for long stretches of time. Mars therefore preserves a record of former habitability, and perhaps of former life if life ever emerged there. Europa enters this comparison from a different direction. The strongest case for Europa is not based on an ancient surface landscape left open to the sky. It is based on the possibility that a habitable environment still exists now, beneath the moon's frozen exterior. NASA describes Europa as an ocean world because many observations are most consistent with a global liquid water ocean under ice. If that interpretation is correct, Europa is not merely a museum of past conditions, it is a place where water may remain liquid, where chemistry may still be active, and where energy may still move through an environment that has lasted for immense spans of time. Scientists often reduce habitability to a few broad requirements, not because life is simple, but because search strategies must begin with what can be tested. One widely used framework asks whether a world has liquid water, the right chemistry, and a usable source of energy. Time matters as well. NASA uses this same general framing for Europa. Water, chemistry, energy, and long duration make a world worth investigating. Europa fits this pattern well enough to justify major exploration. Mars also fits part of it, but much of the strongest Martian evidence points backward toward conditions that were more favorable billions of years ago than they are now. This does not reduce the importance of Mars. In some ways, Mars is easier to study. Its rocks are exposed. Its valleys and crater walls can be mapped in detail. Rovers can drill, scrape, image, and cache samples, sedimentary deposits, which are layers laid down by water or wind, may preserve chemical traces or structural signs of ancient microbial activity. Mars offers direct access to a planetary archive. For this reason, Mars remains one of the best places to search for ancient biosignatures, meaning signs that life may once have existed. Even so, ancient habitability and present habitability are not the same scientific prize. A world that was once suitable for life but later became hostile can still answer major questions about planetary history. A world that may still support life answers a different question. It bears on whether biology can persist beyond Earth in a living environment, rather than only in a fossil record. Scientists do not need to reconstruct every missing step between a distant past and a barren present. They can instead ask whether the required conditions continue to exist. That is one reason Europa can seem more consequential than Mars in the search for living systems. Another reason involves the timescale of stability. Europa is thought to be about as old as Earth. If its hidden ocean has endured for much of that history, then the Moon may have offered liquid water over long periods. Long duration matters because life, as far as science knows, depends not only on ingredients but on continuity. Reactions must proceed again and again. Environments must avoid total sterilization. Energy gradients, meaning differences that can drive chemical work, must remain available. Mars may once have satisfied these conditions at the surface, but the modern planet is cold, dry, and exposed to radiation, with most stable liquid water absent from the surface. Europa, by contrast, may preserve a deep environment buffered from the vacuum of space by ice. There is also an important difference in how each world frames the search itself. Mars is often approached as a world where life, if it existed, may have left traces in rock. Europa is often approached as a world where life, if it exists, may still inhabit water. The first search asks how well a planet preserves evidence from long ago. The second asks whether an environment remains chemically and physically suitable today. Both are scientifically profound. Yet the discovery of life in an active present-day ocean beyond Earth would alter biology and planetary science in an especially direct way. It would show that living systems are not limited to surface sunlight and temperate planetary climates. It would show that a hidden environment far from the sun can still matter biologically. Care is essential here. No observation has shown that life exists on Europa. No measurement has demonstrated a living cell, a metabolism, or a biological ecosystem there. Observations indicate that Europa may possess several ingredients life requires, but it remains uncertain whether those ingredients combine in the right way, at the right places, and for the right lengths of time. The same caution applies to Mars. Mars presents strong evidence for ancient habitable environments, yet no confirmed proof of past Martian life has been found. The comparison between the two worlds is therefore not a contest between certainty and doubt. It is a comparison between two kinds of promising uncertainty. Seen from this outermost level, the reason Europa may matter more than Mars becomes clear. Mars tells a story about a world that appears to have been more hospitable long ago, and now preserves fragments of that history in stone. Europa may tell a story about a world that still holds a potentially habitable environment in the present. One world offers exposed memory, the other may offer ongoing possibility. In the quiet logic of astrobiology, that difference is enough to move Europa toward the center of the search for life. Mars and Europa occupy very different places in the solar system, and that difference shapes nearly every scientific judgment about life. Mars is a planet orbiting the Sun beyond Earth. Europa is a moon orbiting Jupiter far deeper in the cold outer system. Mars belongs to the family of rocky terrestrial planets, with deserts, volcanoes, canyons, dust storms, polar ice, and an atmosphere thin enough to expose the ground to harsh conditions. Europa belongs to a different setting entirely. It is one of the large moons of Jupiter, smaller than Earth's moon in diameter, wrapped in water ice, and known not for a visible landscape of valleys and plains, but for a bright shell that conceals what lies below. From a distance, Mars appears familiar in a way Europa does not. Its day length is close to that of Earth. Its seasons shift as sunlight changes across the year. Its surface can be seen directly from orbit. Dust settles on rocks and gathers into dunes. Ancient river channels, fans, basins, and deltas can be traced across the ground. These features make Mars legible. It presents a world whose geological past can be read from exposed terrain. Even when conditions are severe, the planet seems to belong to the same broad class as Earth, Venus, and Mercury. That likeness has long made Mars the natural first comparison in the search for life. Europa does not invite that same immediate sense of familiarity. It receives far less sunlight. Its surface remains extremely cold. It moves not around the Sun as an independent planet, but around a giant planet whose gravity, radiation, and magnetic influence shape the Moon's environment. Europa's face is bright and smooth compared with many heavily cratered worlds. Instead of broad deserts and mountain chains, it shows a shell of ice crossed by dark lines, disrupted regions, and long fractures. It offers little sign of the open surface water environments that once existed on Mars. At first glance, Mars seems like the easier place to imagine as a cradle for life. This first impression is one reason Mars has held such a strong place in public imagination and in planetary science. Mars appears reachable not only by spacecraft but also by ordinary physical intuition. A human observer can picture standing on its plains, examining rocks, drilling into sediments, and tracing the history of vanished lakes. In this sense, Mars is accessible conceptually as well as technologically. Scientists can investigate it using methods already well developed in geology, climate science, sedimentology, and geochemistry. Sedimentology is the study of how layers of material are transported and deposited, especially by water and wind. On Mars, such layers preserve evidence that liquid water once altered the surface. This makes the planet especially powerful for reconstructing environmental history. Europa demands a different kind of reasoning. It is not studied mainly as an exposed environment, but as a concealed one. Its importance does not depend on a broad record of surface habitability visible in rock layers open to sunlight. Instead, it depends on evidence that the Moon may shelter liquid water beneath its frozen outside. This shifts the scientific comparison at once. Mars is often treated as a world where signs of ancient habitability lie in plain sight, though scattered and altered by time. Europa is treated as a world where present habitability may exist out of sight, protected but hidden. The contrast is not simply between dry and wet, or warm and cold. It is a contrast between an open archive and a sealed environment. The two worlds also differ in the way they preserve or erase evidence. Mars has a thin atmosphere and no global magnetic shield like Earth's. Over immense spans of time, its surface has been exposed to radiation, oxidation, and extreme dryness. Oxidation is a chemical process in which materials react in ways that often strip electrons and transform minerals and organic compounds. These conditions can damage delicate traces of biology. Even so, Mars has rocks, clays, salts, and sediments that may preserve ancient chemical patterns if life once existed. The record is difficult but not inaccessible. Europa may preserve a present environment better than Mars preserves a past one, yet the cost of that protection is distance from direct observation. Ice may shield deeper regions from radiation and vacuum. A deep ocean, if present, may remain stable for immense periods, but the very shell that protects this environment also blocks easy access. The comparison therefore becomes subtle. Mars is easier to inspect but may mainly speak about a lost world. Europa is harder to inspect but may still contain an active one. The scientific value of each place depends on whether the search aims to understand ancient habitability, ancient life, present habitability, or present life. Another contrast lies in the source of environmental change. Mars appears to have undergone planetary transformation across billions of years. Its atmosphere thinned. Surface water became unstable. The climate shifted toward cold aridity. Evidence suggests that early Mars and modern Mars are profoundly different states of the same world. Europa, in the broadest view, may be more constant in the specific sense that its potential ocean environment is not a surface climate exposed directly to the rise and fall of atmospheric pressure. Its possible habitability is thought to depend more on internal and orbital processes than on a mild exterior climate. That difference gives Europa a special place in astrobiology. It broadens the idea of where habitable settings may exist. Mars and Europa also guide the imagination of biology in different ways. On Mars, the most scientifically cautious picture involves microbial life in the distant past, perhaps in lakes, wet sediments, hydrothermal settings, or subsurface niches. On Europa, the cautious picture also begins with microbial life, but in an ocean sealed away from sunlight. This means Mars is often discussed through the language of preservation, fossil traces, mineral context, and ancient environments. Europa is often discussed through the language of oceans, chemistry, long-term stability, and active habitability. The words themselves reveal the different scientific posture each world requires. For all these differences, the comparison is not a dismissal of one world in favor of the other. Mars remains essential because it offers direct evidence that a once wetter and potentially habitable world can evolve into a cold, exposed desert. Europa remains essential because it suggests that a world far from the Sun may still retain conditions life needs. Mars teaches through its open surface and visible history. Europa teaches through its hidden state and persistent possibility. When scientists weigh which world may matter more for the search for life, they are often deciding which is more likely to answer the deeper biological question. Was habitability merely a brief accident on scattered worlds, or can it persist in quiet, concealed places far beyond the familiar inner planets? Far from the region where the rocky planets circle the Sun, the solar system opens into a different kind of domain. The light is weaker there, the warmth that drives weather on Earth, and once as she the giant planets dominate this broad outer region, each with its own family of moons, rings, magnetic influence, and surrounding streams of charged particles. Europa belongs to this distant setting. It is not simply a small world placed farther from the Sun. It is part of a planetary system centered on Jupiter, and that larger setting is essential to understanding why Europa matters. Jupiter itself is immense. It contains most of the planetary mass beyond the Sun, and exerts a strong gravitational command over its surroundings. Around it moves a complex retinue of moons, from tiny irregular objects to large spherical worlds. Among them are the 4 Galilean moons, discovered in the early 17th century and still central to planetary science today. Io, Europa, Ganymede, and Callisto form a miniature system around Jupiter, each different in composition, appearance, and internal history. Together they show that moons around a giant planet can become full planetary environments in their own right. Europa must therefore be understood not as an isolated object, but as one member of a family shaped by common origins and deep contrasts. This Jovian family changes the meaning of distance. In the inner solar system, the Sun is plainly the chief source of surface energy. Earth's climates, Mars's ancient rivers, and even the harsh heat of Mercury all reflect, in different ways, the power of sunlight. In the Jovian realm, sunlight is still present, but much diminished. At Jupiter, the Sun appears far smaller in the sky, and the energy arriving at a moon like Europa is only a small fraction of what Earth receives. This matters because it strips away one of the most familiar assumptions about habitability. A habitable environment does not need to resemble a mild planetary surface lit strongly from above. In the outer solar system, if habitable conditions exist, they do so under very different rules. The outer system is therefore not empty in a scientific sense. It is cold, but it is not simple. Giant planets organize matter into layered systems. They hold rings, shape orbital pathways, influence smaller bodies, and create environments in which moons can follow long and stable histories. Jupiter stands as the clearest example. It is not only a planet but the center of an entire local order. Around it, the Galilean moons occupy distinct positions and show distinct natures. Io is intensely volcanic. Ganymede is the largest moon in the solar system and has its own magnetic field. Callisto preserves an older and more heavily cratered exterior. Europa, bright and icy, sits among them as a world that appears outwardly frozen yet may conceal remarkable activity within. Because of this, scientists often treat the Jupiter system as more than a collection of separate targets. It becomes a natural laboratory. A laboratory is a place where conditions can be compared under shared rules. The Galilean moons likely formed from material associated with Jupiter, yet their later paths diverged sharply. That difference allows planetary science to ask why one moon becomes volcanically extreme, why another grows into a layered icy world, and why another may contain a hidden ocean beneath a frozen shell. In this sense, Europa gains scientific weight from its neighbours as well as from its own properties. It is more informative because it belongs to a system rich in contrast. The Jovian setting also changes how scientists think about life beyond Earth in a wider cosmic sense. For a long time, the search for habitable worlds focused most naturally on planets not too close and not too far from a star, where liquid water could remain stable at the surface. This remains a powerful idea, but the giant planet systems of the outer solar system show that stable liquid water may not depend entirely on surface sunlight. The icy moons broaden the map of possible environments. They suggest that worlds can remain scientifically interesting even when their surfaces are cold and their distance from the Sun is immense. Europa is important partly because it belongs to this broader shift in thinking. It helps move astrobiology away from a single image of habitability and toward a more flexible one. In the Jovian realm, scale also becomes more evident. Jupiter is so large that its moons circle within an environment deeply influenced by the planet rather than the Sun alone. Space near Jupiter is not neutral background. It is structured space, ordered by gravity, magnetism, plasma, and repeated interaction between planet and moons. Europa lives inside that structure, even before one looks closely at the moon itself. The larger environment already suggests that Europa cannot be read by the standards used for Mars. Mars is a planet standing on its own around the Sun. Europa is a moon embedded in a giant planet's sphere of influence. This difference is fundamental rather than incidental. The presence of multiple large icy moons around Jupiter also gives Europa a comparative significance beyond habitability alone. Scientists want to know whether subsurface oceans, if present, are rare accidents or common outcomes in giant planet systems. Ganymede and Callisto are also thought to contain deep internal water layers. Europa becomes especially compelling because its surface appears young and active compared with Callisto, and because its icy exterior seems more directly connected to deeper processes than a quiet, ancient crust would suggest, even without moving inward yet. The Jupiter system already frames Europa as part of a class of worlds that may be widespread both here and around other stars. Thus the broad outer setting matters before any closer examination begins. Europa resides in a darkened region where sunlight weakens, but planetary complexity does not. It belongs to a giant planet's domain, among large moons that reveal many paths of evolution. In that domain, the familiar picture of habitability shifts. Worlds need not be Earth-like at the surface to deserve attention. A moon in the cold outer solar system can become central to the search for life, because the Jovian system itself teaches that distance from the Sun does not end the story. It changes the terms under which the story must be read. Europa moves around Jupiter in a regular and disciplined path. It circles the giant planet once in a little more than 3.5 Earth days, keeping a steady pace through a gravitational field far stronger than the one that governs Earth's moon. This motion is not random and not solitary. Europa belongs to a system in which each large moon follows an orbit shaped not only by Jupiter itself, but also by the repeated influence of neighbouring moons. To understand Europa at this level, the first task is simply to watch its motion, to see the moon not as a still globe but as a body held in constant relationship with a planet and with other satellites around that planet. Europa is also tidally locked. Tidal locking means the moon rotates once on its axis in the same time it takes to complete one orbit around Jupiter. As a result, the same hemisphere always faces the planet. Earth's moon behaves in the same general way with Earth. This locked relationship gives Europa a persistent orientation. One side looks inward toward Jupiter, and the opposite side faces outward into space. The moon therefore does not spin freely with changing faces toward its primary. It turns in step with its own orbital motion, preserving a stable pattern in its day-to-day geometry. If Europa followed a perfectly circular orbit, this lock would produce a simpler mechanical state. The pull from Jupiter would remain more even across time, and the moon's shape would settle toward a more constant equilibrium. But Europa does not move in a perfect circle. Its path is slightly elliptical, meaning slightly stretched. That small departure from circular motion has large consequences. As Europa travels along this elongated route, its distance from Jupiter changes a little. When it is closer, Jupiter's pull becomes stronger. When it is farther away, that pull weakens somewhat. The change is modest in absolute distance, yet the effect is repeated endlessly. The result is a cycle of stress that never fully stops. This repeated stress is the essence of tidal forcing. Tides are not limited to oceans on planetary surfaces. In physics, tides arise whenever gravity pulls more strongly on the near side of a body than on the far side. Jupiter pulls harder on the side of Europa nearest the planet than on the side facing away. That difference stretches the moon. Because Europa's distance from Jupiter changes during each orbit, the amount of stretching also changes. Europa is therefore not held in one fixed shape. It is squeezed and released, stretched and relaxed, over and over again as it moves along its orbital path. The process is subtle in any single moment, but relentless across time. Europa's solid body responds to gravity as a whole object. It does not remain perfectly rigid against this stress. Instead, the changing pull from Jupiter creates a steady rhythm of deformation. The Moon is drawn slightly out of round, then allowed to ease, then drawn again. That rhythm belongs to the orbital pattern itself. One cannot separate Europa's path through space from the forces acting on its body. The orbit is not merely a track, it is a repeating engine of mechanical change. This would already be important if Jupiter alone controlled Europa's motion. Yet the Moon's orbit is also maintained by resonance with neighbouring moons. Resonance is a repeated numerical relationship between orbital periods. Europa is locked into such a pattern with Io and Ganymede. For every orbit Ganymede completes, Europa completes 2 and Io completes 4. This ratio means the moons return to related positions again and again. Their gravitational tugs do not cancel into insignificance. They recur with timing. Over long periods, this repeated timing matters greatly. In many planetary systems, orbits tend to become more circular with time. Repeated flexing and internal dissipation often remove energy from motion in ways that smooth out eccentricity, which is the degree to which an orbit departs from a circle. Europa's orbit might therefore be expected to settle into a more circular path if left alone. But the resonance with Io and Ganymede prevents that complete settling. Each time the moons line up in their recurring pattern, they exchange small gravitational nudges. Those nudges help preserve Europa's slight eccentricity. In this way, the resonance acts as a sustaining influence. It keeps the orbit from becoming fully calm. This fact gives Europa's motion a special character. The orbit is not only elliptical, it is kept elliptical by repeated interaction. The Moon is not passing through a temporary phase on its way toward quiet circular motion. Instead, it occupies a dynamic balance in which orbital stretching is continually renewed. This is why repetition matters so much. A single strong disturbance long ago would not define Europa in the same way. What defines the Moon at this level is the endless recurrence of small, organized forcing. The geometry of the system is therefore inseparable from time. Every few days, Europa returns around Jupiter. Every cycle brings the same basic sequence of changing distance and changing stress. Over many cycles, the Moon also re-enters its resonant relationship with the neighbouring moons. The result is a clockwork pattern, but not a lifeless one. It is orderly motion that produces persistent strain. The precision of the orbit gives rise to physical consequences, not by sudden violence but by exact recurrence. In this sense, Europa's environment is governed by rhythm. This rhythm also distinguishes Europa from Mars in a fundamental way. Mars travels around the Sun as a planet with seasons, atmospheric change, and a largely independent orbital identity. Europa, by contrast, is defined at the larger scale by dependency. Its motion is tied to Jupiter and stabilized through interaction with other moons. It exists inside a network of recurring gravitational relationships. The energy shaping Europa at this level does not come mainly from sunlight falling on an exposed surface. It comes from motion itself, from the fact that the Moon's path is never perfectly circular and never allowed to become so, seen only from the outside. Europa is therefore already more than a frozen moon in a distant orbit. It is a world under organized stress. Jupiter provides the dominant pull. Resonance preserves the slight stretch of the path. Tidal forcing translates that stretched path into repeated deformation. day after day, orbit after orbit. The same pattern continues. Nothing in this large-scale view depends on dramatic change or rare events. The significance lies in persistence. Europa moves, and because it moves in this particular way, gravity continues to work on it with measured repetition. The outer mechanics of the Moon are enough, even by themselves, to explain why Europa is not simply cold and still, but dynamically sustained by motion. Around Europa, space is not empty in the simple sense. It is filled with motion, fields, and charged particles under Jupiter's control. The Moon travels inside one of the most intense radiation environments in the solar system. This radiation does not come chiefly from the Sun. It comes from Jupiter's vast magnetic system, which traps and accelerates particles so effectively that the space near Europa becomes an active physical environment rather than a quiet gap between worlds. Before any attention turns to the Moon's ice or to what may lie below it, this surrounding region must be understood on its own terms. Jupiter possesses a magnetic field of great size and strength. A magnetic field is the region in which magnetic forces act. Around Jupiter, that region extends outward in an enormous structure called the magnetosphere. The magnetosphere is the volume of space dominated by a planet's magnetic field, rather than by the solar wind alone. In Earth's case, this structure is important but comparatively modest. In Jupiter's case, it is immense. It reaches across millions of kilometers and forms a dynamic space environment that contains plasma, radiation belts, electrical currents, and continual interaction with the planet's moons. Plasma is gas in which many atoms are split into charged particles, mainly electrons and ions. In the Jovian system, plasma is abundant. It does not drift passively. Jupiter rotates rapidly, completing one turn in about 10 hours, and this fast rotation helps sweep magnetic structures and trapped particles around the planet. The magnetosphere therefore behaves as a moving system. Charged particles are carried, accelerated, redirected, and energized within it. Europa orbits inside that system, not outside it. The Moon is immersed in a region where magnetic forces and energetic particles are always present. A major contributor to this environment is Io, the innermost of the large Galilean moons. Io is strongly volcanic, and its eruptions release material into space. Some of that material becomes ionized and feeds Jupiter's plasma environment. Ionized means that atoms or molecules gain or lose electrons and become electrically charged. Once this happens, the particles respond to magnetic forces. Over time, this supply helps maintain the energetic population moving through the Jovian system. Europa therefore travels not only near Jupiter's magnetic field, but also within a region partly stocked by matter from another moon. Radiation in this setting consists largely of high-energy electrons and ions trapped by Jupiter's magnetic field. These particles can move at great speed. They spiral along magnetic field lines, bounce between regions, and drift around the planet. The result is not a smooth cloud, but a structured radiation environment with belts and zones of differing intensity. Europa's orbit lies deep enough within this broader system that the Moon repeatedly passes through strong particle flux. Flux is the rate at which particles pass through an area. Near Europa, that rate can be severe enough to shape mission design, instrument protection, and the timing of scientific observations. This is one reason spacecraft visiting Jupiter require special care. Radiation damages electronics, disrupts detectors, and gradually degrades materials. Both NASA and ESA design missions to the Jovian system with this hazard in mind. The danger is not a dramatic burst like a single explosion. It is accumulated exposure, hour by hour, pass by pass. Particles strike sensitive systems and leave behind damage. In the region of Europa, this persistent bombardment becomes a practical limit on how long spacecraft can linger and how close they can repeatedly approach without protection. The radiation environment also reveals something deeper about Europa's setting. It shows that the Moon is not merely orbiting through sunlight and darkness. It moves through a stream of invisible physical influence tied to the giant planet. Jupiter's magnetic field sweeps past Europa continually because the planet rotates faster than the Moon orbits. As a result, the surrounding plasma does not simply wait in place while Europa passes through. Instead, magnetospheric material rushes relative to the Moon, carrying energy and momentum with it. The space around Europa is therefore not still space, it is flowing space. This flow matters scientifically because it shapes what instruments can measure near the Moon. Magnetic observations around Europa must account for the surrounding plasma. Particle detectors must distinguish local conditions from broader Jovian conditions. Instruments looking for signatures of Europa itself must work within a background that is active, variable, and sometimes intense. In this way, the environment around Europa is not merely an obstacle to exploration. It is also part of the subject under study. The Moon and its surrounding space interact continuously, and that interaction carries information. At the broadest level, radiation around Europa does three things. It establishes hazard, it marks Jupiter's dominance, and it creates a setting of constant energetic contact. The hazard is practical and measurable. The dominance is physical, because Europa clearly resides within Jupiter's magnetic domain. The contact is scientific, because energetic particles do not ignore the Moon's presence. They encounter it, respond to it, and help define the space immediately around it. Even before the eye reaches the visible surface, Europa is already being shaped by what moves around it. Yet this harshness should not be misunderstood. Radiation near Europa is severe for exposed materials and for spacecraft electronics, but it does not by itself settle the question of habitability. The relevant point at this outer stage is narrower. The space surrounding Europa is energetic, structured, and continuously active. Any attempt to understand the Moon must begin by recognizing that it exists within a powerful planetary field system. The surrounding radiation is one of the clearest outward signs that Europa belongs to Jupiter in more than an orbital sense. It belongs to Jupiter electrically and magnetically as well. Seen from this region alone, Europa is a moon inside a giant machine of rotating magnetism and trapped particles. The Moon circles through belts of energetic matter that owe their existence to Jupiter's field, rapid spin, and plasma supply. The environment is invisible to ordinary sight, yet it is physically real at every moment. It presses on engineering, observation, and scientific interpretation alike. In the calm logic of planetary science, this surrounding radiation becomes the first close layer of Europa's reality, not the Moon itself yet, but the charged and force-filled space that wraps around it and announces that the Jovian system remains active even where sunlight has greatly faded. Above Europa there is no true sky in the earthly sense. There are no clouds forming from a dense atmosphere, no winds moving across open plains, no pressure deep enough to carry sound or sustain weather. Yet Europa is not entirely bare to space. Around the Moon there exists an extremely thin envelope of gas, so slight that scientists usually describe it as an exosphere rather than a full atmosphere. An exosphere is the outermost and most rarefied kind of gaseous layer, one in which particles are so sparse that they rarely collide with one another before rising, falling, or escaping on Europa. This is the proper way to think about the gas above the surface. It is present, but barely. It surrounds the moon, but not as a stable airy blanket. It is a fragile population of atoms and molecules moving through near vacuum. This distinction matters because the word atmosphere can suggest too much. On Earth, an atmosphere is thick enough to scatter sunlight, support clouds, hold heat, and create pressure at the ground. Even Mars, with its thin air, has dust storms, seasonal pressure changes, and enough gas to affect descent, erosion, and frost behavior. Europa has none of this at the broad scale. Its exosphere is so tenuous that ordinary ideas of weather do not apply. Gas particles do not form a continuous medium. They behave more like individual travelers than members of a shared fluid. Each one follows its own path under the influence of gravity, temperature, and bombardment from the surrounding Jovian environment. Most of this exosphere consists of oxygen, but not in a form that implies biology. It is molecular oxygen produced by physical and chemical processing of water ice. Energetic particles striking Europa's surface break apart water molecules. This process leaves oxygen behind and releases hydrogen more easily into space. Over time, oxygen accumulates as part of the moon's delicate gaseous envelope. This is an important finding, but it must be understood carefully. The presence of oxygen above Europa does not mean that plants or microbes are generating it. It reflects radiation acting on ice, not life acting on a biosphere. The creation of this exosphere is therefore continuous rather than ancient and finished. Europa does not appear to have formed a thick atmosphere long ago and then preserved a remnant of it. Instead, the gas above the moon is replenished through ongoing processes. Radiation from Jupiter's magnetospheric environment strikes the surface and helps free particles from the ice. Some particles are sputtered away, meaning they are knocked loose by energetic impacts. In other cases, solar heating and local conditions may help release small amounts of material. The result is an envelope that is constantly created, constantly lost, and never fully settled. Europa's exosphere is less like a permanent possession and more like a steady transaction between ice and space. Because the gas is so thin, it changes with location and time. It is not expected to remain perfectly uniform around the moon. The hemisphere facing the direction of orbital motion can differ from the hemisphere trailing behind, because each side encounters the surrounding plasma in a different way. Day and night conditions also matter in subtle ways, though not in the manner familiar from worlds with dense atmospheres. The exosphere can become patchy, uneven, and locally variable. It is shaped by where particles are released, by how long they remain gravitationally bound, and by how quickly they are broken apart, ionized, or swept away. Ionization is especially important in this environment. When neutral atoms or molecules lose electrons, they become charged and begin to respond strongly to magnetic and electric forces. Around Europa, this means that part of the exosphere can be transformed into ions and then pulled into the broader plasma flow of Jupiter's magnetosphere. In this way, Europa does not merely wear a gas envelope, it also contributes material to the surrounding space. The boundary between exosphere and space is therefore soft rather than sharp. Gas above Europa is not contained in the way air is contained close to Earth. It shades gradually into the charged and active environment around the moon. Observations also suggest that water vapor may at times be present above Europa, though this remains an area of active study. Some measurements have been interpreted as evidence that water is occasionally released into the space above the Moon. In some cases, this release has been discussed in terms of plumes, meaning localized eruptions or vents of vapor rising above the surface. Observations indicate that such events may occur, but it remains uncertain how frequent, how persistent, and how widespread they are. For this reason, the scientific picture stays careful. Europa clearly possesses a tenuous oxygen exosphere. It may also at times show localized water vapor. The first point is well supported. The second remains under continued investigation. Even without dramatic plume activity, the exosphere is already scientifically rich. It records the ongoing interaction between Europa's outermost solid material and the energetic environment around it. Gas above the Moon acts as a messenger. Its composition, distribution, and changes can reveal what particles are striking the surface, how easily molecules are released, and how the Moon responds to Jupiter's magnetic domain. This makes the exosphere valuable, not because it resembles a habitable atmosphere, but because it preserves evidence of process. It is a thin record written in escaping material. Its thinness also means that survival within it, in any ordinary sense, is not the issue. There is no breathable air, no stable pressure, no temperate aerial zone. The exosphere does not serve as a living environment comparable to the surface air of a planet. Instead, it is a boundary state, an almost atmosphere. It belongs partly to Europa and partly to surrounding space. It is generated at the surface, modified above the surface, and then lost outward. This makes it one of the clearest examples in the solar system of how a world can possess gas without possessing air, in the familiar meaning of the word. Seen at this layer alone, Europa remains a world of restraint and delicacy. The gas above it is real, but sparse beyond ordinary experience. It exists because radiation, ice, and gravity maintain a narrow balance. Molecules are freed, lifted, rearranged, and removed. The whole envelope persists only because the process persists. Europa therefore carries around itself a faint and shifting breath, not as a sign of warmth or weather, but as the most delicate outward expression of continued interaction between the Moon and the space around it. Europa's visible surface presents one of the most distinctive faces in the solar system. Seen from afar, it appears bright, pale, and clean in a way that stands apart from many neighbouring worlds. It does not show the dark basaltic plains of a volcanic moon, the dusty deserts of a rocky planet, or the heavily cratered ancient crust of a quiet outer body. Instead, it reflects sunlight strongly and gives the impression of fresh ice spread across a globe. This brightness is one of the first clues that the surface is dominated by water ice. Water ice reflects much of the sunlight that reaches it, especially when it is relatively clean and recently exposed. Europa therefore shines with an intensity that makes it one of the most reflective large bodies in the solar system. This reflective quality has scientific value beyond appearance. Brightness on a planetary surface often suggests youth, renewal, or both. Over time, exposed surfaces in space tend to darken as they accumulate impact debris, radiation damage, and chemical alteration. A very old surface usually carries the marks of long exposure. Europa's surface, by contrast, retains an unusually bright exterior across much of the Moon. This does not mean every patch is equally fresh, nor that the surface escapes all weathering from space. It means the visible shell has not simply sat untouched for billions of years. Its bright character indicates that ice remains widely present and that the landscape, in broad terms, does not resemble an ancient crust left unchanged since the early solar system. The first close images of Europa transformed the Moon from a bright point of light into a recognizable world. Spacecraft views revealed a surface with relatively few large impact craters compared with many other icy bodies. Craters matter because they serve as a rough measure of surface age. A surface that remains exposed and unchanged for immense spans of time gathers impacts and preserves them. A surface with fewer craters often suggests that it has been resurfaced in some way, erasing or covering older scars. Europa's relative scarcity of craters therefore gives the visible exterior an important quality. It appears geologically young on a global scale. That youth is not measured in the fleeting sense of human time, but in comparison with other ancient planetary crusts that have remained heavily marked by bombardment. Even where impact features exist, they often look softened or modified rather than sharp and permanent. The effect is not the same as erosion by wind or rain, which Europa lacks. Instead, the surface seems to behave as an icy terrain capable of changing its appearance over long intervals. This gives Europa's exterior a restrained smoothness. It is not featureless. In fact, it is richly patterned. Yet its patterns do not generally express the rough, shattered antiquity seen on heavily cratered moons. The overall impression is of a surface that remains active enough, at least in a geological sense, to avoid becoming a static archive of impacts alone. Colour adds another layer to this visible face. Europa is not merely white. Its surface includes pale blues, whites, creams, and yellow-brown tones distributed across lines, patches, and interrupted fields of ice. These variations are subtle at global scale but meaningful. Clean water ice tends toward brightness, while other materials darken or tint parts of the landscape. The colour contrasts make the Moon's exterior readable, even before the exact nature of those materials is examined in detail. Broadly speaking, the surface shows that Europa is not covered by a single uniform frost. It is a varied icy shell in which brightness and darkness map onto differences in exposure, contamination, grain size, and local history. The landscape also gives a strong sense of tension. Long dark markings cross wide distances over the frozen exterior, and broad disrupted areas interrupt smoother plains. At this level of observation, these features shape the character of the surface without yet requiring a full explanation. They tell the eye that Europa's outer skin is not calm in the manner of an old frozen crust. The Moon looks inscribed, as though its bright exterior has been written upon many times. These markings do not create the impression of random scarring alone. They give the surface coherence. Europa looks like a world whose visible layer has been repeatedly modified according to internal rules. Temperature helps explain why ice defines the scene so strongly. Europa receives weak sunlight compared with Earth, and its surface remains extremely cold. Under these conditions, water at the exterior stays frozen hard. There are no open oceans at the top, no rain, and no melting plains under ordinary sunlight. The surface is a cold shell of ice exposed to vacuum, yet cold alone does not produce the pattern seen there. Many cold worlds are dark, heavily cratered, or monotonous. Europa's surface stands out because it combines severe cold with visible freshness and large-scale structure. The ice sees not merely frost but an organized icy terrain. On close inspection, the surface likely differs from place to place in texture. Some regions appear smoother and brighter, others look rougher or more disturbed. Ice can behave in more than one way depending on temperature, impurities, stress, and grain size. Grain size refers to the size of individual crystals or particles making up a material. Fine-grained ice reflects light differently from coarse-grained ice. A landscape built of water ice under constant exposure to radiation and impact gardening, meaning the slow churning of the surface by small impacts, may develop varied textures at scales below immediate visual resolution. Even so, the dominant impression remains one of a frozen exterior that is comparatively young, bright, and regionally diverse. Europa's visible face also resists simple analogies with Earth. Earth ice is usually part of a climate system. It falls as snow, flows as glaciers, melts seasonally, cracks under changing weather, and interacts with air and liquid water. Europa's surface ice exists under vacuum and intense cold, with no dense atmosphere above it. It belongs to an alien setting even when it resembles familiar frozen material. This is one reason the Moon's appearance remains so compelling. It shows a substance well known on Earth, water ice, arranged into a planetary landscape governed by very different conditions. Thus, the bright, frozen exterior of Europa holds scientific importance before any deeper interpretation begins. Its high reflectivity indicates abundant surface ice. Its modest crater count suggests comparative youth. Its varied tones and broad markings show that the shell is neither chemically uniform nor physically still. Its cold exposed plains define a world where water exists at the surface only in solid form, yet does so in a manner that looks renewed rather than anciently exhausted. Europa's surface therefore announces itself as a real landscape, not a simple frozen coating. It is the Moon's first solid region, luminous under distant sunlight, carrying on its face the clear visual signature of an icy world unlike any planet of the inner solar system. Europa's surface does more than reflect light. It also carries chemical information. The frozen exterior is not made of perfectly pure water ice spread evenly across the Moon. Instead, the ice contains a record of mixing, exposure, alteration, and contamination. Some of that record comes from the Moon itself. Some comes from the harsh environment around Jupiter. Some may come from materials that have moved across the surface or been added from outside. At this level, the task is not yet to explain deeper sources in detail, but to read what the visible shell reveals chemically. The surface of Europa is therefore not only a landscape of ice, it is also a chemical skin. Water ice remains the dominant component of the surface. Spectral observations, which study how a material absorbs and reflects different wavelengths of light, show that much of Europa's exterior behaves like frozen water. Spectroscopy is the method used to make such readings. It allows scientists to identify broad classes of material from a distance. On Europa, this method consistently indicates widespread water ice. Yet the same observations also show that the surface is not compositionally uniform. Some regions display signatures that differ from cleaner ice. These places often appear darker or more coloured, especially along major lineaments and disrupted zones. Their spectral behaviour suggests that non-ice materials are present in meaningful amounts. Among the most discussed of these materials are salts. Salt in this context does not refer only to ordinary table salt. It refers more broadly to mineral compounds that can dissolve in water and later remain as residues or frozen components when conditions change. On Europa, scientists have long examined whether parts of the surface contain sulfates, chlorides, or other salts mixed with ice. The exact composition remains an area of study, and interpretations have changed as instruments have improved. Some evidence points toward compounds that include sodium and chloride, while other observations support additional possibilities. What matters most at this level is the broad conclusion that some surface regions likely contain materials more chemically complex than water ice alone. These salts matter because they imply a history of chemical processing. Pure water ice can exist as a straightforward frozen layer, but salt-bearing ice suggests that the material has interacted with dissolved substances at some stage. On Earth, salts in ice often reflect contact with seawater, brines, dust, or rock-derived chemistry. Europa is not Earth, and direct analogy must remain careful. Still, the appearance of salt-like materials on the surface suggests that the Moon's exterior has not been chemically isolated in a simple way. It has undergone processes that introduce or preserve dissolved and frozen compounds. This makes the visible shell scientifically richer than a clean block of water ice would be. Another important part of Europa's surface chemistry comes from radiation products. Jupiter's energetic particles strike the ice and trigger chemical change. Molecules are broken apart and recombined into new forms. This process is called radiolysis. Radiolysis occurs when radiation drives chemical reactions by splitting molecules and creating reactive fragments. On Europa, water ice subjected to constant bombardment can yield oxidants and other chemically altered substances. Oxidants are compounds that readily take electrons from other materials during reactions. Oxygen, hydrogen peroxide, and related products can form in this way at or near the surface. These compounds are important because they represent stored chemical imbalance, and chemical imbalance is often useful for metabolism in living systems on Earth. It is important, however, to keep the meaning of such chemistry precise. Oxidants on Europa's surface do not indicate life. They indicate that radiation is doing chemical work on water ice. The surface is an exposed laboratory where energetic particles continually transform simple molecules into more reactive ones. This is scientifically important because habitability depends in part on available chemistry, not just on the presence of water. A frozen surface continually processed by radiation may accumulate compounds that become relevant to a broader astrobiological picture. But the compounds themselves remain products of physics and chemistry. They are ingredients, not evidence of biology. Sulfur-bearing material may also play a role in Europa's surface chemistry. Some of this material may come from the surrounding Jovian environment, especially through the influence of Io, whose volcanic activity supplies sulfur-rich particles to Jupiter's magnetosphere. These particles can reach Europa and become implanted in the surface. Implantation means that incoming energetic particles lodge within the outer layers of a material. Over time, this process can alter color, texture, and chemistry. If sulfur compounds are indeed present on Europa's surface in significant amounts, then not all important chemistry there originates locally. Some of it reflects the Moon's position inside a larger planetary system, where matter moves from one body to another. The distribution of chemical materials across Europa is also revealing. Cleaner water ice appears more common in some regions, while darker lineaments and disturbed terrains often show stronger signs of non-ice compounds. This pattern suggests that chemistry is linked to geological setting. A region is not dark simply for visual effect. It may contain a different mixture of materials, larger grain sizes, more radiation damage, or more concentrated non-ice compounds. The surface therefore behaves like a map in which colour and spectral character often correspond to real chemical differences. Organic compounds are sometimes included in discussions of Europa as well. Organic chemistry refers to carbon-based molecules, which are important in all known life. Scientists remain interested in whether Europa's surface may contain simple organic material from internal sources, from external delivery by impacts, or from chemical processing at the surface. Observations have suggested the possible presence of carbon-bearing compounds in some places, but the inventory is not fully established. even if organics are present, that alone would not demonstrate life. Organic molecules can form through non-biological processes and are found in many settings across the solar system. Their importance lies in the fact that they enlarge the set of potentially useful ingredients. Thus, Europa's surface chemistry supports habitability in a broad and conditional sense. The ice appears to include water, salts, radiation-made oxidants, and perhaps other chemically useful compounds. This combination makes the exterior more than a frozen barrier. It becomes a chemically active region. Yet caution remains essential. Surface chemistry can indicate ingredients and processes, but it does not by itself reveal whether those ingredients are assembled into living systems or even delivered to the right environments in useful amounts. Observations show that Europa's outer shell is chemically interesting and astrobiologically relevant. It remains uncertain how fully the surface record represents the Moon as a whole. At this layer alone, Europa's ice reads like a sparse but meaningful text. The Moon's bright exterior preserves not just light and fracture patterns, but traces of salts, oxidants, implanted compounds, and altered ice. Radiation rewrites the surface continuously. External particles contribute matter. Local geology organizes where impurities appear. The result is a chemically varied frozen skin that strengthens Europa's importance in the search for life, not because it proves biology, but because it shows that the surface holds many of the raw materials that make habitability worth considering. Europa's surface is not only bright and chemically varied, it is also broken in a way that gives the Moon its most recognizable appearance. Across the icy exterior run long dark markings, narrow bands, doubled ridges, curved fractures, and regions where older patterns appear split apart, shifted, and disturbed. These features cross great distances. Some extend for hundreds or even thousands of kilometers, tracing paths across the Moon like seams in a shell that has endured repeated stress. They do not appear as isolated cracks left by a single accident. They form a global pattern of damage and renewal. The surface looks as though it has been opened, drawn apart, displaced, and then written over again. The most common large features are lineaments, meaning long linear or curving markings that cut across the surface. On Europa, many lineaments appear dark against the brighter surrounding ice. Some occur singly, while others form parallel sets. Their presence immediately distinguishes Europa from a quiet, icy Moon, whose surface would mainly record impacts. These markings show that the visible shell has been shaped by internal and orbital stresses rather than by collision history alone. The eye can follow them over wide areas and see that they belong to the structure of the Moon itself. They are not surface decoration. They are expressions of deformation. Among the most striking of these structures are the double ridges. A ridge is a long raised feature, and on Europa many ridges appear as two roughly parallel crests, separated by a central trough. This paired form gives them a distinct look, as though the surface has been pulled and built upward at the same time. Some rise prominently above the surrounding plains. Others are subtler but still continuous over large distances. They intersect with older terrain, cross younger terrain, and contribute to the strong sense that Europa's exterior has been repeatedly reworked. The fact that ridges are so widespread means that the Moon's outer layer does not remain still for long geological intervals. It is capable of sustained reshaping. Bands add another kind of structure. These features are broader than simple cracks, and often appear as regions where the surface has been opened and filled or rearranged. Their margins can preserve signs that two sides were once joined more closely than they are now. In some places, Surface patterns on opposite sides of a band seem displaced relative to one another, as though parts of the icy shell have shifted laterally before new material or altered ice occupied the gap. This gives Europa a certain resemblance to a puzzle whose pieces have moved, though the comparison must remain limited. The surface is not assembled from rigid blocks in a purely mechanical way. It is an icy terrain under stress, capable of fracture and modification together. The crossing relationships among these features are especially informative. One ridge cuts across another. One dark band interrupts an older line. A disrupted area breaks a pre-existing pattern, then later gains new fractures of its own. In geology, such relationships help establish relative age. If one feature clearly cuts another, the cutting feature must be younger. Europa's surface therefore contains a visible sequence of events, not in exact dates, but in order. The Moon's exterior becomes readable as a history of repeated deformation. No single episode explains the whole landscape. The surface records many stages of cracking, widening, offsetting, and resurfacing. Some regions appear especially disturbed. Instead of orderly lines extending across smooth plains, they show broken blocks, rotated fragments, and hummocky textures, as though parts of the crust have been disrupted and then partly reassembled. These areas are often called chaotic terrain because their structure appears jumbled compared with the more coherent ridged plains. Yet even this apparent chaos follows patterns. Blocks may fit together in incomplete ways. Older surfaces remain visible as isolated plates within newer disturbed material. The results suggest that the visible shell can lose its original arrangement locally without erasing all memory of what came before. Chaos on Europa is therefore not pure disorder. It is disruption with geological meaning. This broken terrain carries an important implication about surface renewal. A surface that is repeatedly fractured, displaced, and modified will not preserve ancient impact scars and original textures indefinitely. Deformation itself becomes a resurfacing process. Even without imagining volcanic eruptions in the usual rocky sense, the exterior can change enough to replace older patterns with newer ones. This helps explain why Europa's visible face appears relatively young. The Moon does not need a dense atmosphere, flowing rivers, or constant meteor bombardment to remake its surface. Stress and ice together are sufficient to generate a dynamic outer landscape. The geometry of many fractures also reflects the broader forces acting on Europa. Cracks do not run in random directions alone. Their orientations vary in ways consistent with repeated global stressing, because Europa is tidally flexed by its orbit around Jupiter. Different parts of the surface experience changing patterns of tension and compression across time. Tension means pulling apart. Compression means pushing together. The icy shell responds by opening fractures, building ridges, and shifting segments along existing weaknesses. The Moon's surface therefore acts as a physical record of stress distribution. The lines across Europa are not only scars, they are traces of force. Colour often strengthens the sense of structure. Darker material commonly concentrates along fractures, bands, and disrupted regions. This makes the broken zone stand out against brighter ice and gives the surface its web-like appearance. The darkness does not merely reveal where the shell is split, it also marks where material properties differ from the surrounding planes. A crack becomes a boundary, both structural and visual. A band becomes an altered region that can be followed across the globe by eye as well as by instrument. This close association between landform and colour makes Europa's surface unusually legible. Deformation and composition appear linked on the frozen exterior. Despite this evidence of repeated change, Europa's landscape does not resemble a place of sudden violence at every moment. The surface tells of long intervals, recurring stress, and cumulative modification. A ridge may take form through repeated action rather than a single event. A band may widen in stages. A chaotic region may reflect prolonged weakening and rearrangement rather than instant collapse. The calm appearance of the moon from far away therefore hides a persistent pattern of slow transformation. Europa's broken terrain speaks in geological time, not in spectacle. This surface record is what makes the idea of exchange so important, even at this strictly exterior level. Exchange here means that Europa's surface does not behave like a sealed and passive crust. It can be opened, altered, and renewed. Material is redistributed laterally. Older terrain is separated and offset. Darker substances appear preferentially along zones of deformation. Disturbed regions interrupt earlier surfaces and create new ones. The visible shell therefore appears capable of movement and reorganization. The Moon's surface is not a final frozen product. It is an active boundary region whose patterns show that change travels through it repeatedly. Taken together, the fractures, bands, double ridges, and chaotic terrains give Europa its essential visual identity. They show a world whose icy exterior has endured systematic deformation on a global scale. The surface is broken, but not ruined. It is disrupted, but not meaningless. Every line as disturbed field contributes to the larger impression of a shell that has been stressed, shifted, and remade many times. In this way, Europa's broken terrain becomes more than scenery. It becomes direct evidence that the Moon's outermost solid layer participates in ongoing geological change. Beneath Europa's visible surface lies the fuller body of the ice shell itself. The bright exterior seen in sunlight is only the upper expression of a thicker frozen layer that extends downward through conditions no camera can observe directly. This shell is not understood as a single uniform slab, identical from top to bottom. Instead, scientists describe it as a structured region whose properties likely change with depth. Near the top, ice is colder and more brittle, meaning it tends to crack when stressed. Deeper down, where temperatures are expected to be higher, the ice may become warmer, softer, and more capable of slow flow. The shell is therefore better imagined as a vertical range of behaviors within one material than as a perfectly rigid lid. Its total thickness remains uncertain. Measurements and models support the idea that Europa's outer shell is substantial, but they do not yet fix one exact value for the whole Moon. Different lines of evidence suggest different possibilities depending on the region, the assumptions used, and the part of the shell being considered. Some interpretations allow a comparatively thinner shell in certain places, while others are more consistent with greater thickness. This uncertainty is scientifically important. A shell only a few kilometers thick behaves very differently from one many tens of kilometers thick. The way stress is transmitted, the ease of fracture, the possibility of internal movement, and the degree of communication between levels within the ice all depend strongly on thickness. Europa's shell is therefore not merely present, its dimensions matter deeply, even while they remain incompletely known. At the uppermost levels, the shell experiences the harshest contrast with space. It is cold, exposed to vacuum, and repeatedly processed by radiation and micrometeorite impacts. In this shallow zone, the ice is expected to act as a rigid material for much of the time. When tidal stresses build and release, the upper shell can fracture, open, and shift. This is the region most directly expressed in the ridges, bands, and broken terrains already visible at the surface. The top of the shell behaves in a way broadly similar to a crust. It preserves structure, accumulates damage, and responds to stress through cracking and displacement. Deeper into the shell, however, the same material may behave differently. Ice is not always hard in the ordinary sense. Over long periods, and under sufficient warmth and pressure, it can deform slowly without breaking. This kind of slow deformation is often called viscous flow. Viscosity refers to resistance to flow. A highly viscous material moves with difficulty but can still creep over time. On Europa, deeper ice may possess this kind of behavior. It may not fracture as readily as the colder near-surface zone. Instead, it may bend, rise, sink, or spread gradually in response to stress and internal temperature differences. The shell thus contains a mechanical contrast between brittle upper ice and warmer, more mobile lower ice. This contrast helps explain why the ice shell is so important scientifically. It is not simply a barrier. It is an active region where temperature, stress, and material properties interact. A purely rigid shell would crack but would have limited ability to reorganize itself internally. A purely soft shell would flow but might not preserve the large fracture systems seen at the surface. Europa's observed landscape suggests a more complex reality. The shell likely includes layers or zones that respond differently to the same forces. Some parts break, some parts deform, some may do both, depending on local conditions. Temperature structure plays a central role in this picture. The shell is coldest at the top, where it loses heat towards space, and warmer at greater depth, where internal heat influences the ice more strongly. This creates a vertical gradient, meaning a progressive change from one state to another with depth. Such gradients matter because they help determine whether ice remains rigid, softens, or begins to move. Even a change of a few tens of degrees can alter how ice responds over long timescales. The shell is therefore not only a frozen layer, it is a thermal structure, organized by the way heat is gained, retained, and lost. That thermal structure may allow internal circulation within the shell. In planetary materials, circulation can occur when warmer, less dense material tends to rise while cooler, denser material tends to sink. In ice, this process is called convection when it happens on a large enough scale. Convection does not mean rapid churning like boiling water. In solid planetary ice, it would be extremely slow, unfolding over long geological intervals. Whether Europa's shell convects strongly, weakly, or only in certain layers remains uncertain. Observations indicate that internal motion within the ice is plausible, but the extent and geometry of that motion are still under study. Even so, the possibility matters because it means the shell may renew itself not only by cracking at the top but also by gradual movement within. Local pockets or lenses of water may also exist within parts of the shell, especially where heating, pressure, or dissolved material change the melting behavior of ice. A lens in this context means a localized body or zone of material distinct from the surrounding layers. Observations of some surface features are consistent with the idea that parts of the shell may contain limited regions of melt or slush, rather than being frozen in the same way throughout. It remains uncertain how common such zones are and how long they persist. Still, this possibility adds to the picture of a shell that is structured and regionally varied rather than perfectly uniform. Impurities further complicate the shell. Salts and other dissolved substances can lower the freezing point of water and alter the strength and behavior of ice. Grain size, crystal orientation, and the presence of fractures or pore spaces also influence how the shell responds to stress. Pore spaces are tiny gaps within a material. On Europa, the shallowest ice may contain damage and porosity generated by surface processing, while deeper ice may become more compact under pressure. This means that the shell's physical character can change not only with temperature, but also with composition and texture. The ice is a material system, not a simple frozen wall. All of this makes exchange within the shell a central idea. Exchange here does not require a fully open pathway from the deepest levels to the surface. It can occur in stages through fracture, migration of brines, slow overturn, localized melting, or movement of warm ice into colder regions. The surface features of Europa suggest that the shell is capable of transmitting change upward and downward within itself. Material may shift from one level to another, heat may be redistributed. Mechanical strain may accumulate in one zone and be released in another. The shell becomes a medium through which the moon organizes stress and matter, not just a passive cover placed over hidden depths. Seen at this level, Europa's ice shell is one of the most important parts of the moon precisely because it is neither static nor simple. It is thick, but not necessarily equally thick everywhere. It is frozen, but not equally rigid throughout. It is cold at the top, warmer below, and likely structured by depth, impurity, and motion. The shell preserves the surface, shapes the surface, and participates in continual internal adjustment. It stands as a world of ice in its own right, with layers, gradients, uncertainties, and slow forms of activity that make Europa far more complex than a frozen sphere viewed only from outside. The case for a hidden ocean inside Europa does not begin with direct sight. No camera has looked through the ice and seen an open body of water spread beneath the shell. The evidence comes instead from several lines of observation that point toward the same broad conclusion. This is common in planetary science. Many important internal structures are known not because they are visible, but because their presence explains measured behavior more convincingly than the alternatives do. In Europa's case, the strongest evidence suggests that beneath the outer ice shell there is a global layer of liquid water containing dissolved salts, and that this layer interacts in measurable ways with Jupiter's magnetic environment. The most important evidence comes from magnetism. A magnetic field can reveal hidden material when that material conducts electricity. Conductivity is the ability of a substance to allow electric current to pass through it. Liquid water by itself conducts only weakly, but salty water conducts much more effectively because dissolved ions carry charge. If Europa contains a broad salty liquid layer beneath its surface, then Jupiter's changing magnetic influence should induce electrical currents within that layer. Induction is the process by which a varying magnetic field generates electrical currents in a conductor. Those currents, in turn, generate their own magnetic response. A spacecraft passing near Europa can measure this response. This is exactly why the magnetic observations from the Galileo mission have been so influential. Galileo flew through the Jovian system and repeatedly measured the magnetic environment near Europa. Jupiter's magnetic field at Europa is not constant in direction and intensity from the Moon's point of view, because the giant planet's magnetic axis is tilted and the Moon moves through a changing field geometry. If Europa were a simple frozen body with no conductive layer inside, the magnetic signature near the Moon would be different from what was measured. Instead, the observations are consistent with Europa producing an induced magnetic field, meaning a secondary magnetic response created inside the Moon by Jupiter's varying external field. This point matters because induction requires a conductive region. The most natural planetary material to provide such a region is salty liquid water. A global ocean beneath the ice offers a straightforward explanation. It would extend around the Moon widely enough to produce a large-scale response, and its dissolved salts would allow electric currents to flow. The magnetic measurements do not by themselves describe every detail of that ocean. They do not show its exact depth in every place, its exact salinity, or the precise thickness of the ice above it, but they strongly support the existence of a conductive shell within Europa, and a salty ocean remains the leading interpretation. The magnetic case gains strength because it fits the Moon's broader character. Europa's surface already suggests that the outer shell has been fractured, shifted, and renewed over time. A world with a thick, fully rigid, entirely frozen interior would be harder to reconcile with such evidence. The combination of a young, icy surface, widespread deformation, and an induced magnetic signature points toward a layered body in which the outer shell is not the whole story. The Moon appears to have a cold exterior and a different interior state beneath it. The magnetic measurements provide the clearest direct geophysical sign of that hidden difference. Geophysics is the study of a world through physical properties such as gravity, magnetism, density, and mechanical response. In Europa's case, geophysics supports the view that the Moon is differentiated. Differentiated means that it is separated into layers by composition and density, rather than remaining a single uniform mixture throughout. This is not unusual for large planetary bodies. Earth is differentiated into crust, mantle, and core. Many moons and planets show similar internal layering. Europa's overall density indicates that it contains both rocky material and a substantial amount of water or ice. The question is not whether water is present in some form, but in what state and where. The evidence increasingly favours a structure in which water exists not only as surface ice, but also as liquid at depth. The shape and surface behaviour of Europa also support this interpretation in a more indirect way. The Moon is close to spherical, which is expected for a body large enough for gravity to pull it into hydrostatic balance. Hydrostatic balance means a state in which gravity shapes a body into an approximately rounded form because the material can yield over long periods. This rounded shape alone does not prove an ocean, but it is consistent with a layered interior. More suggestive is the way the outer shell records repeated global stress. Tidal flexing, surface fracture, and disrupted terrain all make more sense in a world whose icy exterior overlies deeper levels capable of responding differently to heat and force. Some evidence also comes from the Moon's heat budget and long-term physical plausibility. Europa is subject to tidal forcing because of its slightly elliptical orbit and its resonance with neighbouring moons. Repeated gravitational flexing can produce internal heat. The exact amount and distribution remain uncertain, but the process is sufficient to make a buried liquid layer physically reasonable rather than extraordinary. At Europa's distance from the Sun, surface conditions alone would keep water frozen solid. The argument for an internal ocean depends instead on the fact that heat need not come mainly from sunlight. It can arise from the repeated deformation of the Moon itself. This does not prove the ocean independently, but it supports the internal logic of the ocean model. There are, however, important uncertainties. Magnetic measurements show a conductive region, but conductivity alone does not fix every detail of composition and geometry. In principle, other conductive materials could contribute to the signal. Scientists therefore evaluate which explanation best fits the full body of evidence. A global salty ocean beneath the ice remains the most widely accepted answer because it explains the magnetic response in a simple and physically plausible way, while also matching what is known about Europa's density, surface youth, and tidal environment. The alternative explanations are generally less comprehensive or less consistent with the whole set of observations. It is also important to state what the evidence does not yet provide. It does not directly map the full ocean floor. It does not reveal every variation in ice thickness above the liquid. It does not show whether the water is equally deep everywhere. It does not determine all chemical conditions within the hidden layer. The scientific case is strong, but it is not complete in every detail. Observations indicate that Europa likely contains a global salty ocean beneath its icy shell. It remains uncertain exactly how thick the shell is in every region, how the ocean circulates, and how strongly different layers communicate with one another. Even with these limits, the evidence for a hidden ocean stands as one of the most important discoveries in the study of icy moons. Europa is no longer understood as a solid frozen body all the way through. The moon is instead interpreted as a layered world, whose outer ice covers a conductive liquid region beneath. The magnetic field provides the clearest geophysical sign. The surface geology supports the broader picture. Tidal heating makes the existence of such a layer physically credible. Together, these lines of evidence create a calm but powerful conclusion. Beneath Europa's bright fractured shell, there is strong reason to believe that a global ocean is present, concealed from view yet detectable through the disciplined language of physics. Once the hidden ocean is accepted as the leading interpretation, Europa changes meaning. It is no longer simply an icy moon with a remarkable surface. It becomes a world defined in large part by liquid water. That shift is profound because liquid water remains central to the scientific idea of habitability. Water is not treated as important merely because life on Earth depends on it. It is important because it is an unusually capable medium for chemistry. It dissolves substances, transports materials, moderates temperature change, and allows molecules to meet, separate, and react. A world with a long-lived body of liquid water is therefore not automatically alive, but it becomes far more scientifically significant than a world that is only frozen through and through. Europa's ocean is thought to be global rather than local. This means it likely extends around the moon beneath the ice shell instead of existing only in isolated pockets. A global ocean changes the scale of the environment at once. It suggests continuity, not scattered reservoirs. If liquid water occupies a layer that circles much of the moon, then Europa contains not a few hidden lakes but an immense connected water system. Estimates of total water volume vary depending on the thickness of the ice and the depth of the ocean, but many models imply that Europa may contain more liquid water than Earth's oceans combined. The exact amount remains uncertain. The broader conclusion is that this is not a marginal feature. It is one of the moon's defining internal regions. Scale alone does not create habitability, yet it matters. A very small body of liquid might freeze quickly, become chemically exhausted, or remain too isolated for sustained environmental stability. A vast ocean behaves differently. It can store heat more effectively. It can sustain gradients in temperature and composition from one place to another. It can persist through long spans of planetary history if the surrounding conditions allow it to remain liquid. Europa's ocean therefore attracts scientific attention not only because it exists, but because it may exist on a scale large enough to remain stable over immense periods. Persistence is among the most important features of all. In astrobiology, time is not a minor detail. Living systems do not arise in an instant and do not continue without continuity of conditions. The longer a habitable environment lasts, the more opportunity chemistry has to proceed through repeated cycles. Europa appears to offer this possibility. The Moon is ancient, like other major bodies of the solar system, and if its ocean has endured through much of that history, then the ocean represents a stable environment measured not in thousands or millions, but potentially in billions of years. That timescale alone raises Europa's importance. A deep and long-lived ocean provides the one condition that makes all other astrobiological questions worth asking seriously duration. The ocean is also significant because it is protected. On Earth, surface environments are shaped constantly by weather, ultraviolet light, seasonal change, and the many disturbances of an open planetary exterior. Europa's ocean lies beneath ice, and that ice serves as shielding. Shielding means protection from external radiation and from direct exposure to space. This does not make the ocean gentle in every respect. It only means that it is buffered from some of the most sterilizing conditions affecting the surface, while Europa's exterior endures intense radiation from Jupiter's magnetospheric environment. The buried ocean is separated from that exposure by a thick frozen cover. The ocean is therefore not merely liquid water in a distant moon. It is liquid water held in relative environmental stability beneath a protective shell. Salinity is another important part of the picture. Salinity refers to the concentration of dissolved salts in water. The ocean beneath Europa's ice is widely thought to contain dissolved ions, which is one reason it conducts electricity well enough to support the magnetic evidence for induction. The exact composition and concentration remain uncertain. It is not yet known whether Europa's ocean resembles Earth's seawater closely, differs from it greatly, or varies significantly from place to place. Still, the probable presence of salts matters because dissolved substances alter the freezing point, density, chemical reactivity, and circulation behavior of water. An ocean that is chemically active and saline is more interesting astrobiologically than one consisting of nearly pure liquid alone. At the same time, salinity introduces complexity rather than simple advantage. Water can contain too few dissolved substances to support rich chemistry, or so many that the environment becomes more difficult for biology as it is known on Earth. Scientists therefore avoid easy assumptions. Observations indicate that Europa's ocean is likely salty. It remains uncertain whether its salinity falls within a range favourable to life. How that salinity is distributed and how it has changed over time. Even so, the presence of dissolved ions means the ocean is not chemically blank. It is a medium with structure and potential. Temperature within the ocean is also unlikely to be uniform. In any large body of water, differences in heat, salinity, and pressure can create zones with distinct properties. Europa's ocean exists under high pressure because of the great weight of ice above it. Pressure is the force exerted over an area, and in deep planetary oceans it becomes substantial. High pressure does not by itself exclude habitability. Earth's deep oceans support life under pressures once thought prohibitive. On Europa, pressure simply becomes part of the environment that any biological or pre-biological chemistry would have to inhabit. The ocean is therefore not best imagined as a calm and featureless chamber of water. It is a layered fluid world with its own internal conditions. The absence of sunlight at depth also changes the meaning of the ocean as habitat. On Earth, the familiar image of life often begins with surface light, photosynthesis, and food webs ultimately linked to the sun. Europa's ocean lies beneath enough ice that sunlight does not define it in the ordinary way. Yet the scientific importance of the ocean does not depend on sunlight reaching through. What matters first is that liquid water can remain present for long intervals in a chemically active state. This broadens habitability beyond the most familiar surface model. Europa's ocean is significant because it shows that a living environment, if one exists there, would be based on a different planetary arrangement. For all these reasons, the ocean beneath Europa is treated as habitat in the potential sense. It is not known to be inhabited. It is not proven to contain the full combination of conditions life requires. But it is large, persistent, shielded, and likely saline. It appears to offer a stable liquid domain lasting over geological time. That combination is rare and scientifically powerful. In the search for life, many worlds offer fragments of the needed picture. Europa may offer one of the most complete hidden settings, yet identified beyond Earth, not visible, not confirmed as living, but sustained enough to deserve the full seriousness of astrobiological attention. Liquid water alone does not make a world habitable. Chemistry alone does not make it habitable either. A living system requires a way to do work, and in biology that work depends on energy moving through an environment in usable form. This is why Europa's hidden ocean is scientifically important not only as a body of water, but as a possible energetic system. The question is not whether energy exists somewhere in the Jovian system. Energy is everywhere in physics. The question is whether Europa's ocean contains forms of energy that can support sustained chemical activity of the kind living organisms could use. In the dark beneath the ice, that question becomes central. On Earth, the most familiar biological energy source is sunlight. Light from the sun powers photosynthesis at the surface and in shallow water. Photosynthesis is the process by which organisms use light to build energy-rich molecules from simpler substances. Much of Earth's biosphere rests directly or indirectly on that foundation. Europa's ocean does not. The ice above it is too thick for ordinary sunlight to define the ocean as it defines Earth's surface life. This does not make Europa irrelevant to biology. It simply means that any usable energy must come through other pathways. The search for life there becomes a search for chemical energy in darkness. Chemical energy becomes available when substances are out of balance with one another. This condition is often described as disequilibrium. Disequilibrium means that matter is arranged in a way that allows reactions to proceed and release usable energy as the system moves toward a more stable state. Living organisms on Earth often exploit such imbalances. They do not create energy from nothing. They tap differences that already exist in the environment. The more stable and renewed these differences are, the more promising the environment becomes. Europa's importance depends in part on whether its ocean maintains such differences over long timescales. One of the most significant possibilities involves oxidants produced near the surface. Europa's outer ice is continually processed by radiation. Energetic particles break apart water molecules and create reactive products such as oxygen-bearing compounds and hydrogen peroxide. These substances matter because oxidants can accept electrons in chemical reactions. Electron transfer lies at the heart of metabolism. If oxidants formed at or near the surface are transported downward into the ocean in meaningful amounts, they could provide one side of an energy-yielding chemical system. In broad terms, they would represent chemically useful material created high in the icy shell and then introduced into deeper water. This possibility is scientifically attractive because it links the harshness of the surface to the potential habitability of the ocean. Radiation at the exterior may damage exposed material, but it also manufactures reactive compounds. If some of those compounds travel downward, the surface ceases to be only a barrier. It becomes part of the Moon's energy economy. Yet the key uncertainty is transport. Observations indicate that oxidants can form at the surface, but it remains uncertain how efficiently they move through the ice, how often they reach the ocean, and in what quantities they remain chemically available once they arrive. An energetic ingredient exists. Its delivery remains an open problem. Energy in the ocean also depends on renewal. A single deposit of reactive material would not sustain biology for long. Life requires continuing gradients, continuing supply, and continuing removal of spent products. Europa becomes more interesting if chemical differences are not merely present but replenished. This is why circulation matters even within a hidden ocean. Water that moves can redistribute heat, dissolved compounds, and reactive substances from one region to another. Circulation does not need to be violent to be important. Slow motion over long intervals is enough to maintain contact between regions of differing chemistry. A chemically quiet ocean might remain liquid yet energetically poor. A circulating ocean has a better chance of preserving useful imbalance. Tidal forcing contributes to this picture by providing ongoing internal energy to the Moon as a whole. Europa is flexed repeatedly by Jupiter's gravity because of its slightly elliptical orbit. That flexing generates heat within the Moon and helps prevent its water from freezing solid. In this sense, tidal energy underlies the entire environment. It does not serve biology in the direct way a nutrient or oxidant might. It acts more broadly, keeping the system active enough for liquid water, internal motion, and chemical cycling to persist. Without this continuing mechanical input, Europa's ocean would be far less plausible as a long-lived habitat. Radiolysis may also matter in a more limited and careful sense. Radiation can split molecules and create reactive fragments, not only at the surface but also in shallow zones where energetic particles penetrate. This process can store energy chemically by producing compounds that later participate in reactions. At Europa, the greatest importance of radiolysis is generally thought to lie near the exterior, where radiation exposure is strongest. Scientists therefore treat it less as a complete energy solution and more as one part of a broader system of chemical activation. It may help load the upper ice with reactive species. Whether that loading contributes substantially to the deeper ocean depends again on transport and mixing. Earth offers a useful comparison, though not a direct model. In the deep ocean on Earth, some ecosystems live without sunlight and rely instead on chemical energy. This is called chemosynthesis, meaning the biological use of chemical reactions rather than light to build organic matter. The existence of such life shows that darkness alone does not exclude biology. What matters is the availability of compounds that can react in energy-releasing ways. Europa's ocean is scientifically compelling, because it may also be a place where chemistry rather than sunlight sets the terms of habitability. The analogy remains limited because Europa differs from Earth in pressure, composition, temperature, and planetary context. Still, the basic lesson is important. A dark ocean can remain biologically interesting if energy gradients endure. The term gradient is central here. A gradient is difference across space, such as a difference in concentration, temperature, or electrical state. Biology often depends on gradients because they allow ordered work to occur. In Europa's ocean, the most important gradients may be redox gradients, meaning differences between oxidizing and reducing conditions. Oxidizing conditions favor the removal of electrons. Reducing conditions favor their donation. When both kinds of chemistry meet in sustained ways, metabolism becomes more plausible. Whether Europa possesses strong and stable redox gradients remains uncertain, but the Moon's surface processing, internal activity, and long-lived liquid water make the question scientifically meaningful. Thus, energy in Europa's darkness is best understood not as one dramatic source, but as a network of possibilities. Surface radiation creates reactive compounds. Transport through ice may move some of them downward. Ocean circulation may redistribute chemicals and maintain contact between different regions. Tidal flexing supplies long-term internal energy to the system as a whole. Radiolysis adds further chemical activation near exposed layers. None of this proves life. None of it guarantees that the ocean contains enough usable energy in the right places for biology to arise or persist. But it does show that Europa's ocean is not merely wet. It may also be chemically awake, with ongoing processes that keep energy available in forms more subtle than sunlight, yet potentially no less important for habitability. At the bottom of Europa's ocean, the liquid water is expected to meet rock. This boundary is one of the most important places in the entire Moon. Above it lies the deep global ocean, dark and pressurized beneath the ice. Below it lies the rocky interior, denser and more mineral-rich than the frozen shell above. Where water and rock remain in contact over long spans of time, chemistry becomes more than a passive background. It becomes an active exchange between materials in different states. For astrobiology, this matters because water-rock interaction is one of the clearest known ways to generate chemical diversity and usable energy without relying on sunlight. Scientists are confident that Europa has a rocky interior beneath its water layer. The Moon's density shows that it cannot be made of ice alone. A substantial fraction of its mass must consist of silicate rock, and likely a metallic core deeper still. Silicate rock is the common rocky material made largely of silicon and oxygen combined with metals such as magnesium and iron. On Europa, this rocky part of the Moon is not a minor inclusion. It is the deep structural foundation beneath the ocean. The question is not whether rock exists there, but what kind of contact it maintains with the overlying water and how chemically active that contact may be. Water-rock interaction begins simply. Liquid water touching mineral surfaces dissolves some substances, alters others, and creates new compounds through reaction. Over time, the rock can be transformed chemically, and the water can become enriched with dissolved ions and gases. On Earth, this process occurs in many settings, from groundwater moving through crust to hot water, circulating through the ocean floor. At Europa, similar principles may operate at the base of the ocean, though under different pressures, temperatures, and compositions. Even without extreme heat, prolonged contact between saline water and fresh mineral surfaces can create a chemically interesting environment. One especially important process is serpentinization. Serpentinization is a reaction in which certain water-rich minerals form when liquid water interacts with iron and magnesium-bearing rock. During this process, the rock changes, and hydrogen can be produced. Hydrogen is important because it is a strong reducing agent, meaning it can donate electrons in chemical reactions. Where hydrogen is available alongside oxidants or carbon-bearing compounds, metabolism like chemistry becomes more plausible. On Earth, microorganisms are known to exploit such chemical differences in dark environments. This is why Europa's rocky seafloor attracts so much attention. It may provide not just a place for contact, but a place where electron donors are continually generated. Hydrothermal activity is another major possibility. A hydrothermal system is one in which water is heated by internal energy, circulates through rock, and returns carrying dissolved minerals and altered chemistry. On Earth, hydrothermal vents occur along parts of the ocean floor where heat from the interior drives water through cracks and porous rock. These systems create local environments rich in chemical gradients. Europa may host analogous activity if enough heat reaches parts of the rocky interior, and if water is able to circulate through fractures or porous regions there. Observations do not yet prove active hydrothermal vents on Europa's seafloor, but scientists regard them as plausible. If they exist, they would make the ocean floor one of the Moon's most energetic and chemically diverse regions. Tidal heating strengthens this possibility. Europa is flexed repeatedly by Jupiter's gravity, and that flexing can generate heat not only in the ice shell, but deeper inside the Moon as well. The exact distribution of that heat remains uncertain. Some may be concentrated more in the ice, some in the rocky interior, and some may vary over time. Even so, the repeated mechanical stressing of the Moon makes internal warmth more credible than it would be in a completely inactive frozen world. Heat at the rock-water boundary would matter because it could drive circulation, open reaction pathways, and maintain localized environments where chemistry is constantly renewed rather than left to stagnate. Porosity is an important part of this deeper picture. Porosity refers to the presence of tiny spaces or channels within rock. A porous rocky interior allows water to penetrate, circulate, and react with a large surface area of mineral material. This can greatly increase the extent of chemical exchange. A dense, sealed rock layer would still interact with the ocean at its surface, but a fractured or porous seafloor would permit far more extensive water-rock reactions. Scientists do not yet know exactly how porous Europa's rocky interior is, nor how that porosity changes with depth and time. But the more connected the rocky material is to circulating water, the greater the potential for sustained geochemical activity. Carbon chemistry may also enter here. Carbon-bearing compounds are central to biology on Earth, but they need not arise through life. Water rock systems can help transform inorganic carbon into more reduced forms under the right conditions. Reduced here means richer in electrons and therefore more chemically reactive in certain pathways. On Europa, if carbon compounds are present in the ocean or delivered through the Moon's history, the seafloor may be one of the places where they are altered into more useful chemical forms. This does not imply that complex biology must follow. It means only that the rocky interior could help turn a simple ocean into a chemically structured one. The rocky floor also matters because it offers surfaces. Chemistry in open water can proceed, but mineral surfaces often help organize reactions, concentrate substances, or promote the formation of particular compounds. On Earth, many hypotheses about the origin of life give an important role to minerals, pores, and interfaces between water and rock. These ideas remain under study, yet they share a general point. A world of liquid water alone is less chemically interesting than a world where liquid water repeatedly meets reactive rock. Europa's seafloor, if active and accessible to circulating water, provides exactly that kind of interface. Pressure at these depths would be immense, but high pressure does not remove scientific interest. It changes the rules of chemistry and mineral stability. Yet Earth already shows that life can persist in deep marine settings under great pressure. Europa would not replicate those conditions exactly. Its ocean depth, salt content, internal heat flow, and gravity differ from Earth's. Still, the lesson remains. The deep ocean floor is not automatically sterile simply because it is dark and compressed. Under the right chemical circumstances, it can be one of the most promising habitats available. Uncertainty remains substantial. Scientists do not yet know whether Europa's seafloor hosts vigorous hydrothermal venting, low-temperature water-rock exchange, patchy reaction zones, or some combination of these. They do not know how much hydrogen may be generated, how efficiently chemical products are mixed into the broader ocean, or how stable such activity has been over time. Observations indicate that a rocky seafloor exists and that water-rock interaction is plausible and likely important. It remains uncertain how intense, widespread, or continuous that interaction is. Even with these uncertainties, the significance of the rocky interior is clear. At the base of Europa's ocean lies the region most capable of supplying reducing power, mineral diversity, and long-lived chemical gradients. It is the place where the Moon's deepest solid matter meets its hidden global water. There, pressure, heat, porosity, and mineral reaction may combine to create an environment more chemically fertile than any quiet body of liquid alone. For the search for life, this deepest boundary is not merely the bottom of the ocean. It is one of the strongest reasons Europa is taken so seriously as a potentially habitable world. At the deepest point of this inward path, the question becomes simple in form, even if it remains difficult in science. Why might Europa matter more than Mars for the search for life? By the time the comparison reaches this stage, the answer no longer depends on visual familiarity, public imagination, or ease of exploration. It depends on what kind of biological question each world is best suited to address. Mars and Europa are both among the most important places beyond Earth in astrobiology. Each one may answer a profound question, yet they do not offer the same question in the same way. Mars is a world of exposed history. Its ancient river valleys, lake basins, sedimentary layers, altered minerals, and preserved rocks point to a planet that once held liquid water at the surface. Observations indicate that early Mars possessed habitable environments in the distant past, perhaps for long enough intervals to allow prebiotic chemistry or even simple life to emerge. This makes Mars one of the best places in the solar system to search for ancient biosignatures, meaning traces that life may once have left behind. A biosignature may be chemical, mineral, isotopic, or structural, provided it is better explained by biology than by non-biological processes. On Mars, the great scientific hope is that some part of the ancient record remains preserved well enough to test that possibility. This is an extraordinary goal. If Mars once hosted life, and still preserves evidence of it in rock, then biology would no longer be a phenomenon known only from Earth. Even a fossil or chemical trace from a vanished Martian biosphere would alter science permanently. It would show that life emerged at least twice within one planetary system, or that conditions favourable to life are more common than once assumed. Mars therefore does not become less important simply because its strongest promise may lie in the past. A dead biosphere, if it once existed, would still be a discovery of immense consequence. Europa, however, may matter more for a different reason. Its greatest promise lies not in preserved ancient habitability alone, but in the possibility of a habitable environment that still exists now. Beneath the Moon's ice shell, observations indicate that a global salty ocean is likely present. That ocean may have endured for immense spans of time. It may contain a continuing supply of chemical ingredients. It may be supported by internal energy from tidal forcing and by chemical interaction between water and rock at depth. These conditions do not prove life. Yet taken together, they place Europa in a category that is rare and scientifically powerful, a world that may still possess a living environment in the present. This distinction changes the meaning of discovery. Ancient life and present life are not equivalent finds, even though both would be transformative. Ancient life answers whether biology once emerged elsewhere. Present life answers whether biology can endure elsewhere, in an environment still active today. The first result expands the history of life. The second expands its current reality. A confirmed living system in Europa's ocean would show that life is not confined to warm planetary surfaces under direct sunlight. It would show that biology can persist in a hidden ocean beneath ice, far from the inner solar system, sustained by chemistry and internal energy rather than by surface climate. This would widen the known range of habitable settings much more sharply than a fossil record alone. Europa also matters more in one additional sense. Mars, for all its richness, may require scientists to reconstruct a lost world from partial remains. Rivers are gone, lakes are gone. The climate that shaped the most habitable periods is gone. The work on Mars is therefore partly forensic. It studies clues, remnants, mineral memories, and geological preservation. Europa may allow a different kind of science. If its ocean remains active, then the object of study is not only a record but an ongoing system. Scientists would not merely ask what conditions used to be. They would ask what conditions still are. That shift from reconstruction to present environment makes Europa especially compelling. There is another reason for caution and balance. Europa is much harder to access. Its ocean lies beneath a thick shell of ice. The radiation environment around the Moon is severe. Direct sampling of the buried water is far beyond the reach of ordinary observation. Mars, by comparison, offers open ground, visible strata, and a surface that rovers can traverse. The practical search for evidence is therefore easier on Mars in many respects. Ease of access does not make Mars more biologically important in principle, but it does make Mars more immediately testable. This is why the scientific comparison remains measured. Europa may matter more conceptually for the search for living systems, while Mars may remain more accessible for the search for preserved signs of past life. The contrast can therefore be stated clearly. Mars is the stronger target for ancient habitability and ancient biosignatures. Europa may be the stronger target for present habitability and perhaps present life. One world preserves former environments in rock. The other may sustain an active environment in water now. One offers open archives. The other may shelter ongoing chemistry beyond direct sight. One tells of what a planetary surface once was. The other asks what a hidden ocean may still be. Neither replaces the other. Each world tests a different edge of biology's possible range. For astrobiology as a whole, Europa's importance also reaches beyond the solar system. If a moon in the dark outer reaches around a giant planet can host a long-lived ocean with the ingredients and energy needed for life, then habitable environments may be more widespread in the universe than surface-focused thinking once allowed. Many planetary systems may contain icy moons or ocean worlds that never resemble Earth from the outside. They may lack blue skies, exposed continents, and temperate surface seas, yet still maintain deep liquid environments over billions of years. Europa stands at the threshold of this broader idea. It suggests that the universe may support hidden habitats in places once dismissed as too cold and too distant. This is why Europa could matter more than Mars in the search for life. Mars remains indispensable because it preserves the ancient question so well. Europa may matter more because it preserves the living question itself, not whether water once crossed a vanished surface, but whether a dark ocean still endures. Not whether habitability briefly visited a planet long ago, but whether it can persist in silence beneath ice for ages beyond ordinary imagining. In that calm and exact sense, Europa becomes more than a moon of Jupiter. It becomes one of the most important tests of whether life belongs only to Earth's familiar surface world, or to a wider and stranger order of nature. The thought settles into quiet proportions. Mars keeps its deserts, its dry deltas, its stone memory of running water. Europa keeps its brightness, its fractured shell, its hidden sea. Both remain among the great destinations of science. One asks what life may have once done. The other asks what life may still be doing, beyond sight, in darkness, under pressure, within a world of ice and salt and rock. The search does not choose between wonder and evidence. It moves carefully toward places where the conditions are strongest and the questions are deepest. In that movement, Europa holds an unusual gravity. It is not the easiest world to read, and not the nearest in feeling. Yet it may be the one that most directly tests whether life can persist far from the sun in an ocean no eye has seen. Beneath that idea there is a deeper stillness. A frozen moon circles a giant planet in the cold outer system. Around it moves radiation and magnetism. At its surface lies fractured ice. Below the surface, a shell. Beneath the shell, a long ocean. At the bottom, rock and chemical change. Nothing in this layered world promises life. Nothing in it rules life out. Science remains patient there. It proceeds by evidence, by comparison, by cautious inference. And in that patience, Europa continues to matter, not as a symbol, but as a real place where one of the oldest human questions meets one of the most unusual environments yet known.